So in this video, let's do a few more examples of using definite integrals to find the area between functions. And the first example that I would like to consider is find the area between the functions y equals x and y equals x cubed on the interval from 0 to 4. And once again, I do strongly recommend to begin the process by graphing these two functions, just to have a clearer idea of what is going on. I have our straight line, y equals x, and we have our cubic function, y equals x cubed, which wiggles through the origin. And we are interested in the integral from 0 to 4. Now, what's interesting about this example is that roughly halfway through the region at x equals 1, the role of the top function swaps from originally from 0 to 1, y equals x is on the top, but as x becomes larger than 1, the cubic function is the one that's on the top. Blue then overtakes green and is on the top of this region. So to reflect that, to calculate this area, we're going to have to do two integrals. One integral in the case that x is between 0 and 1, where the function x is the top function. And a second integral on the interval 1 to 4, where the function x cubed is the top function. Then, having established these two intervals, we can evaluate each of them separately. For the first integral, we have x squared over 2 minus x to the 4th over 4, evaluated from 0 to 1. And for the second part of this integral, we have x to the 4th over 4 minus x squared over 2, evaluated from 1 to 4. So, plugging in these numbers and taking the difference will give us the final answer for this question. Here, x equals 1 gets plugged in, 1 to the 4th over 4. If I plug in x equals 0, both of these terms will vanish, so I don't have to worry about that. Plug in x equals 4, and then subtract what I get when I plug in x equals 1. 1 to the 4th power over 4, 1 to the 2nd power over 2. Now this can be simplified as much as you like, and when simplified, the number that you get as a result of those calculations will give you the area between these graphs, not only on the region 0 to 1, but also on the region from 1 to 4, where the role of the top and bottom function have been swapped. As a similar example, let's consider the following. Find the area of the triangle bounded by the three lines y equals 1, y equals 2x, and y equals negative x plus 3. And as always, I'm going to go in and I'm going to get myself a little drawing. So here is y equals 1, horizontal line, constant function. And here, coming in with slope 2, a line through the origin, y equals 2x. And then, coming in with negative slope 1, starting out at y equals 3, we have y equals negative x plus 3. And the triangular region bounded by these three functions is given here in gray. Now, if we are going to use a definite integral to calculate this area, we're going to have to be careful, because once again, there's a change in the top function midway through the region of integration. For a short time, the red function, y equals 2x, is on the top of the region. But after I pass this corner, the blue function, y equals negative x plus 3, is on the top of the region. So I expect to have two integrals. One at some limits where 2x is the top function and 1 is the bottom function. And then another integral where negative x plus 3 is the top function and 1 is the bottom function. So let's now try and find the values of x that I could use to fill in these limits of integration appropriately. Now the region begins at this point of intersection between y equals 2x and the green line y equals 1. So if I set 2x equal to 1, the point where those lines intersect have an x value of 1/2. That's where that first region begins. Now this second x value of interest occurs at this point where the red line and the blue line intersect one another. So to reflect that intersection, I'll set 2x equal to negative x plus 3, and this has the solution x equals 1. So this transitional point occurs at x equals 1. So that is where the first half of the triangle left off and where the second half of the triangle begins. Finally, we have this region of intersection between the green line and the blue line. That represents the end of the region. If I set negative x plus 3 equal to 1 to reflect that intersection, then I will get a value of 3 minus 1, or 2, is equal to x. And that's the end of the region of integration. Now, just as before, now that we have established who is the top function, who is the bottom function, and what are the limits of integration, we can go through this process of finding and plugging values into the antiderivatives. So for the first function, antiderivative of 2x minus 1, my favorite antiderivative is x squared minus x. And we would be evaluating that from 1/2 to 1. And then for the area of the second part of the triangle, we would have an antiderivative of negative x squared over over 2. And the plus 3 minus 1 would combine to a plus 2, whose antiderivative is 2x. Then, after plugging in top and bottom limits of integration, 1 squared minus 1, 1/2 squared minus half, that's this first antiderivative, and plugging in the second limits, negative 2 squared over 2 plus 2 times 2, take away negative 1 squared over 2 plus 2 times 1, this sum total, the result of this calculation, will give us the area of the triangular region bounded by these three lines.